into a little bit more detail about Beer's law. So Beer's law, A, absorbance equals the molar absorptivity times the path length times the concentration. So simple, what could go wrong, right? Well, let's consider an instrument where you have the source and a monochromator and the sample and then the detector, just like what we've talked about before. So, but this time, we can actually increase reproducibility and get better statistics if we add a reference cell, and then we use these cuvettes often come, like fancy cuvettes, come as matched pairs so that they're perfectly optically matched. So then we if we put in this reference cell, then we can do a little bit better job, we can do a little bit better with our statistics. All right, so Beer's law, so simple. What could go wrong? Well, actually, there's a lot of things. Beer's law is very powerful, but at the same time, you have to be a little bit careful and a little bit aware of what the pitfalls are of Beer's law. So, one could be too little absorbance. It's hard to differentiate if there's very, very little sample between the reference and the sample itself. So it's hard to quantify if there's very little. You can also have too much absorbance, and it's hard to differentiate between, you know, a absorbance of 0.9999 and 0.9998 or something. So when you have very, very little transmitted light, it's actually very difficult to see small differences. So the best range for modern spectrometers is between 2 and 0.03. So you want to stay in that range. I usually like to stay below 1. And so you want to dilute, if you have any power over this at all, you want to dilute so that your absorbance is between, I think, 1 and 0.3 is a good range. So you also want to make sure that you're analyzing at lambda max, because not analyzing at lambda max, which we'll see on the next slide, is kind of bad. You also want to minimize stray light or scatterable light, so you want to keep your sample box closed up. Oftentimes you see them painted black on the inside to minimize any kind of light that might scatter off the front of the cuvette or off of other optical, so that it would be absorbed by the instrument walls as opposed to getting bounced all around and potentially getting detected. You also want to make sure that if you're doing very precise measurements, that you have well-matched cuvettes for your sample and your reference. Alright, so what happens if you don't analyze at lambda max? So say you were so here's lambda max of this absorbance peak, and here's lambda not max. So if you have a little bit of drift in your monochromator, you know, your lambda changes a little bit, or you have this band that I'm showing, so oftentimes you don't have exactly monochromatic light. And so if you have a little bit of broadening of this band, a few more wavelengths getting in, at lambda max it's not such a big deal. You can see that broadening this or moving it around a little bit would not cause a huge change in absorbance. But if you were here and you had a little bit of broadening or a little shift, you would have a much greater change in the absorbance. And so you definitely want to make sure that you're analyzing at lambda max whenever possible. Let's talk about Beer's law in the context of analyzing a mixture. So say you have a mixture of a couple of different analytes in solution. So the absorption is actually is related to the sum of the molar absorptivities times path lengths times concentrations of each of the species in solution. So here's, if you have overlapping peaks, you can just analyze the absorbance at a bunch of different points for your mixture. And so this is showing the blue and the green teal curves are actually just the two analytes that are mixed in solution. So if you measure the absorbance at a bunch of different points of each end member, each of the analytes in solution, as well as the mixture, then you would be able to deconvolute that and quantify how much of each species is in the mixture. Another sort of special case of this is when you have a mixture of two species. And so if you have several mixtures with different concentrations of the two species, you might see something like this, where you have one species and then the other species. And if you have something that's called an isobestic point, where all of the curves cross right there all together, that's some really good. That's a really good indication of your mixture just containing two components. All right.